For coming. Tonight we have a very exciting event. Join me to welcome Trent. Round of applause. Trent is a reference in blockchain ecosystem. He was the CTO and founder of BigChainDB and now of Ocean Protocol, two very exciting projects. The intersection between AI data and blockchain, and we're very happy to co-organize this with cryptoeconomics.hub. Again, amazing event. So thank you very much for coming, and I hope you're going to enjoy.
Yeah, just a quick word. Sandra, the co-organizer of cryptoeconomics.hub, is about to join us, but she's still in the metro. So I'm going to do the introduction. Just a little bit of background about what we do. So cryptoeconomics.hub, it's a hub that we created a little bit more than a year ago now, after studying for another year or so on Ethereum mainly, but blockchain in general. And we came to realize that the most fundamental knowledge that you can bring to this space is related to how you build those systems from the ground up. And in addition to that, there is maybe a scientific approach, something that can be done more methodologically. And therefore, cryptoeconomics was a good opportunity at the time to get into the fundamentals of why do we get the properties and hopefully the desirable outcomes from those economic networks that we are trying to build. And Sandra was actually in Paris a couple of months ago, where she met Trent. And that was, I think, mostly the time where the token engineering thing came up, right, and was introduced. And I let her keep explaining the story. And so, yeah, just the idea is to see what are the common points between the two fields, maybe cryptoeconomics and token engineering, whereby I think you can get with cryptoeconomics a good base layer for networks and economic interactions to happen in a decentralized fashion. And then the token engineering, I see it as a very good approach to build further tokens on top of this base layer with the same kind of quality standards required for cryptoeconomics. And I let Sandra introduce the talk of tonight.
Okay, so I'm really sorry for being late. Welcome everybody, also from my side. I don't want to talk a lot because I want that you talk actually the most. Just to let you know, I assume you all are familiar with Trent, so I guess you know who he is. He has a PhD in artificial intelligence, or he focused on research on in this sector before blockchain, and now he is involved in the Ocean Protocol and in BlockchainDB and in all these fantastic projects. And we actually met at the Ethereum conference in Paris and had a wonderful chat about cryptoeconomics. And I told him, please, whenever you can, come to Madrid, because we would love to hear you here in person. And and that's it. So I let it now to you to talk.
All right, guys. Really a pleasure to be here. I'm Trent, as I guess I've been introduced. So thank you, Sandra, and the rest of you for having me. It's a pleasure to come and hang out in beautiful Madrid with mostly beautiful weather. All the weather is more beautiful than Canada, rural Canada in the wintertime, let me tell you. But we won't focus on Canadian weather. We're going to focus on blockchain and specifically token engineering today. So let's get started. And I'm going to start with sort of an intro around data and incentives. And a quick aside, by the way, you're going to see a lot of jellyfish. And you might ask, what's with all the jellyfish? And the answer is, if you could imagine an animal, that AI being an animal, what would that animal be? And to me, it's a jellyfish. They're kind of like the epitome of an animal that kind of looks AI-like, especially the ones that look like they have the LED lights and stuff, which aren't really jellyfish, but they look like it. So anyway, think of, every time you see jellyfish, think AI, okay? So, and also it fits with ocean and all that, of course. So let's rewind to the late 90s, mid 90s. I got a job working with the Canadian government doing AI, actually. I was still an undergrad, and I couldn't believe that people would pay me to work on artificial intelligence. So of course I worked as hard as I could and all that. And the task that I was given was, it was around audio radar classification. So I was given 20,000 data points and 13 classes. And I had a time series signal coming in. And from that time series signal of audio radar, sort of like a thing you can listen to, it might be going tuck, 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 tuck. And the machine, the AI machine, the classifier has to decide, is this someone walking? Is this birds flying? Is this a tank driving, etc.? And the reason is, overall, right now in tanks, you have two people. You have one guy listening to radar, like that guy there, trying to decide, is it birds, is it tanks, whatever outside, and you have another person driving the tank and figuring out the rest. And they wanted to basically say, can we have just one person total? So I was given these 20,000 data points, and I had to come up with this machine. At the beginning of the summer, as a reference, I just made a simple linear model. And the accuracy was 55%. So it was failing almost half the time, right? So completely useless. After 4 hard months of work and toiling and playing with neural networks and genetic programming and all of this, and I had great fun. At the end of the summer, my accuracy was 65%. So 1/3 of the time, it was still failing. And of course, that was not shippable, that was not usable. And I finished that job and it was never deployed. And the thing is, this was actually the state of the art of AI in the late 90s. There was lots of research, lots of papers published, but it was nowhere close to being usable, right? And now and then there was an application that managed to sneak through that was actually accurate enough, et cetera. But you can't ship a product that fails 1/3 of the time. You really need failure of 1% or 0.1%, right, or better. But then along came some research coming out of Microsoft in the early 2000s. This is a picture from a paper by Banquo and Brill in 2001. And they showed something remarkable. The x-axis here is the number of data points, millions of words in this case. It's a language problem. And the y-axis is the accuracy, okay? So throughout the 90s and even before, people doing AI would focus on these data points and the 4 data points in the far left, right? So those are 4 different algorithms. You've got a KNN, perceptron, a couple other ones, right? And people would always focus on having a small data set. In this case, it's 200,000 words. And they would say, hey, look, I've got 55% accuracy. Hey, look, I've got 71% accuracy. But the problem is, all these models are terrible. None of them are deployable. None of them are useless. And you could get conference publications over this, but it was just not useful. But what these guys discovered was, you know what? Let's not, spend a summer job of 4 months or even a PhD to invent a fancy new algorithm to improve by 5%. Let's just add more data. And not just 2x more data, but 5x, 10x, 100x, 1,000x more data points. Keep the algorithms the same. What happens? Well, as you add more data, the accuracy goes up, 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 all the way up to 99%. And it didn't even matter what algorithm they used, all of them kept improving. And in fact, the simpler ones worked a little better as they went farther along. So the one that did the best is algorithms from basically the 50s, right? And if you think about it, AI people do not want to admit this, right? Because they want to justify their existence as, hey, I did a PhD to get this amazing accuracy, right? So even myself, as a person who did AI for almost 20 years, it's kind of embarrassing, right? But at the same time, you have to say, well, look, it works. I'm going to use this. I'm going to deploy it. Because first and foremost, I'm an engineer. I like to build things. I like to ship. So these researchers at Microsoft published this remarkable paper, and then others started to notice. And in about 2005, some researchers at Google published a paper called The Unreasonable Effectiveness of Data. Peter Norvig, very famous from the AI world, and some others. And it was sort of like an atom bomb in the field, actually. At first, it was sort of quiet within circles in Google. And actually, I learned from a Google researcher friend about the paper. But within 2, 3, 4 years, basically, people were adopting it because they really wanted to ship these systems. And over time, basically, people started realizing, hey, if we have larger and larger and larger neural networks, then we're going to have even more and more accuracy. And this is where deep learning came from. Deep learning is actually basically neural network architectures of the early 60s with Moore's law. Moore's law to handle more data, to handle more training in reasonable time, right? So, and not just 10x more data, but 10,000x more data. So when Google and Facebook and all these guys call themselves AI companies, they're actually not. That's a head fake. They're actually data companies. Google buys satellite imaging companies. Microsoft buys Skype. Why? For better data, so that they can get higher and higher accuracy, just like this. And so they've, overall then, the strategy of these very large companies, they've gotten very large because they have tons and tons of data that they've been gathering for 10 years plus. And they have the AI algorithms, the expertise in order to deploy these, in order to get the value. So their game is more data means more accuracy, which means selling more ads or whatever else, which means more money, right? Close that loop, 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 and you get remarkably powerful. They call it the data network effect, right? And so this picture is from the Economist article, May of 2017, where it basically talked about data as the new oil, as powering this new economy around data, right? And of course, if you're Facebook, why would you want to share your data with Google or with anyone else so that they can sell more ads? Of course not. You're incentivized to hoard your data, to maintain that data silo, right? And of course, this is a problem for us as people, as citizens of the planet, because now we have these large companies that are basically trying to like sneak in and grab our data and not tell us about what's going on. And thank goodness for laws like GDPR, so we actually start to see more of what's going on. But of course, you know, Facebook, in the light of GDPR, they gave this posting of like, okay, we're basically stealing your data, but so say yes or no, right? And everyone clicked yes, of course, right? You know, so maybe over time it will start to fade away, but overall, now we know we're being people farmed, whereas before we were being people farmed without knowing, right? So, but the fact of the matter is we're being people farmed. Oh, and by the way, you remember PRISM with Snowden? That didn't go away, right? It's still here, worse than ever. So, so if you think about it, though, what's going on? And there's a really great summary, and that is a wonderful quote from Charlie Munger, who worked with Warren Buffett for decades and decades on, you know, one of the world's largest and most successful investment funds. Show me the incentive, and I will show you the outcome, right? It all comes down to the incentives, right? So if you think about these large companies with these data silos, they are incentivized at the end of the day to increase the value of their shares. How do they do that? More profit, more revenue, all of that. How do they do that? More data, right? So they are incentivized to gather more data and to keep it from others, right? That's the summary. Then the question is, well, what can we do about this? You know, as people, as technologists, as, you know, basically hopeful builders of the future, right? And until recently, the way to handle this was, you know, go to the government and say, please, 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 can you change these rules? And, you know, now and then really positive things happen, like GDPR, but that's pretty rare, right? You know, next month there's a law coming down through the EU about copyright, and it's actually really bad, right? So while GDPR is good, other laws aren't so good, so, you know, it's kind of a coin toss, and this stuff takes 5 years or 25 years to happen, right? Imagine instead where we can actually start to structure the incentives more directly, rather than relying on governments to shape economic institutions, to shape, you know, the rules of business, et cetera. Imagine if we, as technologists, as builders, could actually come up with machines that shape the incentives directly. It's actually possible now. It's possible to build incentive machines, aka blockchains. So when people talk about blockchains, normally, you know, there's been all this rhetoric around ICOs and, you know, when Moon and cryptocurrency and the price of Bitcoin and the price of Ether and stuff, or even maybe benefits, right? Things like provenance and immutability. And, you know, those are really nice benefits, right? Really great benefits. But there's one benefit that's actually talked about not as much as it should, and it really is the superpower of blockchains, the most important thing. And that is the incentives superpower, right? How do you summarize that? You can get people to do stuff by rewarding them with tokens. Where do those tokens come from? The network prints it, magic internet money. But you know what? It's not really that magic, it's just a shared belief in the value of that token. No different than the US dollar. The US dollar has been off gold since the early 70s, right? It's a shared belief in the value of that token in a community. Whether it's America, whether it's a bunch of people who believe in the future of Bitcoin or the future of Ethereum or whatever, right? So to summarize, there's this superpower that these incentive machines manifest, these blockchains, and that superpower is getting people to do stuff. But that raises the question, okay, we have this superpower, we have this new machine, this new tool. What do we want them to do? What would we like to do to make the world a better place, right? Well, in the case of data, which, you know, powers the economy, it's pretty important. Let's use it to change the incentives from data silos to pooling the data, to democratizing data, to making it available for everyone if they want, and at the same time giving control of personal data back to the people. Sovereign, self-sovereign data, right? So that's really the goal that we have with Ocean. And That's basically what we've been striving towards for a while, and this is sort of in line with sort of my own career as well of, starting out in the late 90s, as I described, doing AI, building a couple of AI companies throughout the 2000s, going into blockchain in 2013. Back then, no one barely heard of Bitcoin, let alone blockchain. So, blockchain industry, there was no industry, right? There's a handful of crazy people like us and others that were saying blockchain, blockchain, and everyone else is like, blockchain, we don't even know what Bitcoin is, right? But bit by bit, people figured it out, and now we no longer have to teach people about blockchain, which is great. But now, now that sort of some of these base systems are getting more mature and good enough, Ethereum didn't even exist when we were working on this. So now, though, that you have things like Ethereum as a substrate that's programmable and you can build smart contract systems on top, what do those smart contract systems look like? Well, they are token economies, right? They are these incentive machines. So we have substrates like Ethereum. How do we build those incentive machines? And that's what we set out to do with Ocean about a year ago, saying, okay, we want to have this incentive machine to change the Schelling point, to change the default incentive from siloing data to making it more available to everyone, to democratizing it, right? So we started out and, started like good engineers, we got in front of a whiteboard and started writing out a bunch of things, right? And here, this was actually several sessions worth of things. So on the top right, for example, is an algorithm to automatically compute the relative impact of different data sets into an AI model. Because, let's say you have a royalty scheme and you're giving 20% of all proceeds of the AI person to the data people. Then are you going to give, maybe you have 5 data providers, are you going to give equal value to each data provider? What if one data set has all the impact? So of course you needed an algorithm for that. So we worked out that algorithm. And it was pretty straightforward because other people had done stuff before. I even did some stuff like that in the 2000s. And there's a bunch of other stuff too. I think other slides zoom in. No. So other slides, like in the very, very center, it's this idea of, what if I serve up data that someone promises to be private, but then they take that data and then they put it all public through the whole world, right? What if you could make it where if they make that data public, they're accidentally giving away their private key and then anyone can go in and take all their Bitcoin or whatever, right? So, and it turns out you can actually do that. There's a scheme for that. And there's a bunch of other things we did here, right? And explored. And we were exploring other things too, like, what about tokenizing access to the data itself? Or can you ICO a data set, right? Or, what if we made the token model of Ocean to be just like Steemit, right? Where it's sort of like you contribute and there's some curation going on and so on. Or what about a pricing scheme? What about the price of data itself? Should we have a fixed price and that's it? Should we allow an auction? But auctions imply that the data is fungible, right? But every data set might be unique. So then what do you do, right? And what if there's really only one buyer in the end? What about reverse auctions? All of these things, right? So we were asking a lot of questions, and friends were coming in from all over the world. Lots of people come into Berlin to kind of hang out and talk and learn about blockchain and crypto, right? And usually to come and hang out at Room 77, the first place in the world, the first bricks and mortar place in the world to accept Bitcoin for anything, right? And Room 77 not only accepts Bitcoin for anything, it accepts Bitcoin for beer. So when I moved to Berlin in 2013, basically I was very happy because here was this place that you could go and hang out with people, have some beer and talk about Bitcoin and blockchain. So anyway, that still happens, and we had friends coming in and gave us feedback, right? And we started trying to zoom in on, adding a bit of rigor. So on the bottom left here, it's a whole list of different signals going into and out of the system. For example, can you stake the belief in the value of a data set? What about the price asked by a buyer? What about the price bid, and so on, right? But what we realized was we didn't know when we would stop, right? We started to realize, we're flailing. So we'd been doing this for a couple months, 3 months, and when did we know that we were done? Right? When did we know that we felt comfortable with the design? We had never done it before ourselves. And even the people who had it was sort of like a one-off, like friends, say with Augur, they'd been at it for years, or Gnosis, or all these other ones, right? So what do we do? Can we structure this better? Can we start to have a methodology, right? And we were starting to realize this sort of June, July last year, right? And then though, we kind of started realizing, around the same time, we started realizing tokenized ecosystems are a lot like evolutionary algorithms. And it wasn't just us, it was friends like Simon Delervier from Ujo and some others. It's sort of like you have this evolutionary aspect going on, evolution as in survival of the fittest, right? And so I'll draw some parallels here. And maybe, actually before I do, I'll jump back again. Before I do, I'm going to briefly describe an evolutionary algorithm. So it's an algorithm, it's this an optimization algorithm from the branch of AI where you're trying to evolve, say, a circuit. So the resistances of in fact, I won't use a circuit, I'll use a car, it's simpler yet. So let's say you're a car designer, you're working for, say, Chevrolet out of Detroit, right? And you want to maximize the fuel efficiency and minimize the weight, say, right? Maybe maximize the top speed. And what are the parameters you can play with? Well, you can change the wheel diameter, you can change the size of the engine, and you can even drill down and do other things, right? So you're trying to wiggle these different parameters, and you're trying to, according to these objectives and constraints, right? Like maybe constraint of it has to hold 5 people, right? And it has to be sufficiently safe, et cetera. And then as you wiggle these parameters, you end up with a design that's optimal in some ways, right? So maybe it's maximizing fuel efficiency subject to these other constraints, or even a whole trade-off. And this is the practice of optimization, right? And engineers do this daily in all these different engineering fields, whether it's car design, whether it's circuit design, or whatever, right? And in fact, throughout the 2000s, I was building tools for circuit designers to do things like this. So under the hood, when an engineer says, I want to optimize this, they actually can run an optimizer. It's an automated algorithm that says, press a button, and then it runs a simulator for, say, a car or a circuit. It says, okay, given that the wheel displacement is given that the wheel diameter is, say, 18 inches and the displacement is, say, 3 liters, then it's going to have a top speed of, say, 180 kilometers an hour, right? And then if you increase the displacement a bit, the top speed goes up. So this optimizer runs these simulators in the loop and optimizes. And in the end, you get something, well, that's better, right? So one of the types of optimizers is evolutionary algorithms. So with a car design example, it's simply where you have, say, a population of 100 different car designs. This one has this wheel diameter, and this one has this wheel diameter, and so on. And they're all running around doing their own thing. And then every generation, you simulate each one, and you say, okay, now of these guys, which you keep the best half. So 50% you get rid of, and you keep the best half, and they get to make babies, okay? But those babies are slightly different. They mutate a bit. The wheel diameter changes a bit, or the engine displacement goes up a bit, or whatever. And then basically you repeat. So the babies and the parents, they run again, you simulate them, and then you see who's the best again. And then you repeat again, and again, and again, over 50 generations or 500 generations. So this is an evolutionary algorithm for designing cars or for circuits or whatever, right? It's a very standard thing. It's been around since the 70s, basically. And they keep getting better, and there's a very active field of research, thousands of researchers that do this, right? So, and I had done a lot of this too in my PhD. Now, what I started realizing, and a couple other friends, was, you know what? These tokenized ecosystems, these blockchain ecosystems, are a lot like evolutionary algorithms. And here's how. So we have these goals, right? So with evolutionary algorithms, it might be, for example, maximize the top speed, right? Well, with a blockchain, say Bitcoin is trying to say, you know what? I want to maximize security, which is minimizing the chance that people can unroll the list of transactions, right? How does it maximize security? It's maximizing the hash rate, right? So they both have goals. And then basically you have a way to measure those goals, okay? So in the case of evolutionary algorithms, it's running a car simulator or running a circuit simulator. With tokenized ecosystems like Bitcoin, it's actually the proof. So proof of work in Bitcoin, proof that you solved this crypto puzzle. Or in the case of, say, Steemit, it's actually proof that a person contributed some human work to write this blog post, right? Or in Augur, it's actually proof that you made an observation, you're getting paid to make an observation, right? And so on and so forth. So there's measurement and test in both cases. Then you have basically these agents running around. So for the circuit simulator, you have these agents, which are candidate car designs. And they have, they can kind of do whatever they want. At the end of the day, they just get exposed to the simulator to get measured. Same thing in the world of blockchains. You have miners running around, people running around doing whatever. And really, Bitcoin doesn't really care. Ethereum doesn't really care. All they really care is, at the end of the day, if you contribute value to the ecosystem in the form of, in the case of Bitcoin, proof of work, then I'm going to give you rewards, right? That's it. So the blockchain doesn't care at all about what those agents do otherwise. At the end of the day, they reward for that. So they incentivize you to add value to the ecosystem, just like evolutionary algorithms. You can't control the individuals. All you can do is reward when they do well, or punish if they do badly, right? So in the case of evolutionary algorithms, if you do badly, you just die, right? In the case of blockchains, if you do badly, well, you don't die generally. Maybe there's a future blockchain like that, but hopefully not. But generally, there are ways to punish bad behavior, things like slashing stake or kicking you out of a token-curated registry or something. So overall, basically, what this means is you have these two ecosystems that are a lot like each other. And there's a way to summarize this. They are both manifestations of evolution, right? So a tokenized ecosystem isn't just a simulated evolution. It's actually a real thing. You can't turn it off. There's no way. It just keeps running and running and running, just like actual evolution, right? So, and that also means something else amazing, right? It means that we can, if we're trying to design these tokenized ecosystems, we can approach token design as optimization design, as design of optimization algorithms, evolutionary algorithms to be precise, right? So what I'm going to do now is actually just quickly review how do you go about designing an optimization algorithm. And I'll show it's simple. And from that, I'm going to show how we can port those ideas, those best practices from the field of optimization to token design. And then I'll give some examples. So in optimization design, it's 3 steps. Formulate the problem, try an existing solver, and if needed, only if needed, do you design a new solver, right? So formulate the problem comes down to the objectives, constraints, and design space. Objectives are things you want to maximize or minimize. So in the case of a car, you're trying to maximize top speed. So you just say, OK, I'm trying to maximize top speed. A constraint is something like saying, OK, I have 4 people, right? I need to fit at least 4 people, or I need to fit no more than 4 people as well. So it can be inequality or equality constraints. This is a picture here of just a screenshot from a paper doing optimization, where the F is the objective functions, the things to maximize and minimize. The G and the H are inequality and equality constraints. And then the bottom thing is simply the design space that the optimizer is allowed to run around in. For example, the range of possible wheel diameters, et cetera, right? And any paper that does optimization, you'll see something like this, right? And then what it does is it defines what F means for the context of this particular paper, right? And so this case, in this is a paper on circuits that I wrote many years ago. And then you try an existing solver, right? In this case, it's showing the x-axis, which is time, so generations of an evolutionary algorithm, and the y-axis is cost, so trying to minimize cost. There's 20 runs here, and you can see about 10 runs converge pretty well. And the other 10, they go to the far right, and they don't converge. They don't go to a cost of 0. So from 20 different runs, it's doing OK half the time. Now, in the case of a tokenized ecosystem, remember, you basically only get 1 run, right? You launch this thing, and it goes. So if it has only a 50% chance of succeeding, that's probably not very good. So you're going to probably want to design your system better so that it has a better chance of converging. So in general, though, you try this solver, and you see, does it converge, yes or no? If it does, great. Guess what? You can stop. It's working. But if it doesn't, then you should try different things. So you can try a different solver. So maybe, for example, at first you say, OK, I've got this very simple linear programming solver. You should always try the simplest thing that could possibly work first, right? So you try something linear, it fails, you're like, great, I'll try quadratic optimization or something. So like some Newton descent method, for example. And if that doesn't work, then you get something more and more general, maybe resorting to an evolutionary algorithm. The other thing you can do is change the problem itself, right? So for example, if you can actually, rather than some sort of super general problem that you can't assume anything, if you can assume that it's a linear problem, like one big plane, then it's super simple to solve, right? You can solve it in polynomial time. And in the 90s, people realized that if you manage to cast things as one big hill, a convex optimization problem, then you can also solve that in polynomial time by basically tweaking some linear programming algorithms into basically convex optimization. So if you can cast a general nonlinear problem into something that is convex optimization, that's really great news, because you can solve it maybe in 10 seconds instead of 10 days, right? So that's the tricks, right? You try a solver. If it doesn't work, you try to change the solver or the problem formulation, right? But sometimes that doesn't work either. And then you have to resort to step 3, which is design your own new solver, right? And it's really, really tempting to do this first because it's fun, right? So you sit down and you're like, oh, I've got this new problem, and I want to spend the next 2 months or 3 years of my life for this PhD to come up with this whole new cool solver and write a couple papers in this conference publication and so on, right? And by the way, this is a great KPI in academia, but it doesn't matter at all if you're trying to ship something for the real world that works. And I'm talking about token engineering here, okay? So I'm not talking and I'll get into this later, but I love science, The goal of science is new knowledge. The goal of engineering is to build things that work in the real world, right? So, and they go hand in hand. You know, they're twins, they're siblings, all of that. So here, this is an example of a solver. This is from my PhD. I did get to hide in a corner for a while and play with algorithms. And I very explicitly chose to do stuff in my PhD that would not be rewarding in industry. Because you know, I knew that if I was trying to do it in industry, it would fail. Or maybe it would work, but I didn't want that constraint. And actually, frankly, at the same time, I was doing a startup solving a different problem that was pragmatic. So I had PhD and company at the same time. So here's a solver that, to this day, has never been deployed in industry. And I didn't care because I was doing it for my PhD. But you shouldn't confuse these things, right? Anyway, I designed the solver, and it worked really well. So it had some really nice successful outcomes. It was, you know, synthesizing some circuits and all that, right? And then in the end, I'm like, hey, good, I'm done. The solver worked. I knew what I was aiming for. Great. But I only did that knowing that I was in for a long run and for my PhD, right? So I'll just summarize this again here. Optimization design, formulate the problem, try an existing solver. If needed, change the problem, change the solver. And only if needed do you design a new solver. And what you do not want to do is ignore all the steps and just start playing with new solvers at first. And by the way, this is what every new PhD student does who's doing algorithms. They just start playing with stuff for 6 months or a year. And actually, honestly, that's okay to play. You learn a lot quickly. But if you really want to like ship something that works or something that's useful, then you know it's more useful to start to add some rigor. What are you aiming for? Try using existing patterns that are known to work, and only if needed, add new patterns. So guess what? We can actually transfer this to token design. And it looks almost identical, right? Formulate the problem, try an existing pattern or building block, and then only if needed do you do a new building block, right? And you have to have the courage, even if you're like, oh, we need a new building block because we're trying to raise $100 million for our ICO. Guess what? Do a TCR, tell everyone it's going to work because it's probably going to work or something. And that's a lot better than having something fancy that you spend 4 years to build and never, ever, ever ship, right? Okay? So I'll go into the details of this, but the summary is, just like optimization design, these steps. I'm not saying this is the be-all, end-all method. I'm saying this is what we discovered worked for us in the context of Ocean, and actually several projects since that we've helped with. I view this as sort of like, you know, the first 0.1% of this emerging field of token engineering, and I'll get more into that later too. So this is not the be-all, end-all, but it's a practical methodology to help design. So let's drill into each of these. So formulating the problem. In the case of tokenized ecosystems, you can drill into this very specifically. First question, who are my potential stakeholders? So in the case of, and I will give examples later, but you know, it's not just the miners. What about the people that you know want to get utility from the system? Maybe suppliers in some way, consumers in some way. There's also the hodlers and the investors and so on. What does each of them want? What can each of them give? What are their gives and gets, right? And also, what are possible attack vectors? And from that, by asking with each stakeholder the gives and the gets, and with the attack vectors, we can translate that into objectives and constraints, or at least candidate objectives and constraints, okay? Attack vectors, each one is a constraint. And you can choose whether or not to solve it, right? You don't have to solve it. In fact, you know, as Bitcoin was maturing, there was lots of people speculating about different attack vectors. But you know, the Bitcoin core team didn't go in and try to address every attack vector because some of those attack vectors never actually manifested in reality. So you don't have to try to solve everything. You want to have a pragmatic design that reconciles with simplicity too, right? And I will give examples on this, but just to start now, that's the step. And then the step 2 is try existing patterns, right? And it turns out that in the last year and a half, there have been a lot of patterns emerging. And I mean, many of you have probably talked about and seen that here in this group. Sometimes they're called cryptoeconomic primitives, and that's a really good description for the sort of leaf node patterns. But of course, you can combine primitives to higher and higher building blocks as well, right? So there's patterns with respect to curation, things like token-curated registries. There's patterns for proofs of work, whether it's human-based or compute-based. You know, Bitcoin proof of work is one example. There's patterns for identity, for reputation, for governance, for third-party arbitration, and so on, right? So there's this growing set of patterns of building blocks, okay? And to drill down into a couple, for example, in curation, one that's become very popular, in fact, there was a recent hackathon called ETH Denver for Ethereum. 1/3 of all the participating teams used token-curated registries. And it's basically a membership in a set. Are you in or are you out? It was developed very much by AdChain, which is sort of this ad exchange. In their case, it's a list of good links that you're able to have ads on there versus bad links that are really spammy or attack sites or something, right? And there's basically staking mechanisms to get into this registry, and there's challenge or response sort of things, and so on. And that's whether you're in or you're out. And then you can get a bit more fancy. I say discrete valued here. That's really DAG valued. You can literally have a bunch of stake machines where it's this directed acyclic graph, and you can go from one entry in the graph to the next via some sort of staking mechanism or other things. And there's also sort of shades of gray in between. You can have a layered TCR, you can have a graded TCR. There's a bunch that have been emerging. And there's other patterns too. Curation markets have really started to explode, and they're really about continuous valued membership, and so on and so forth. I'm going to point to resources later that you guys can use, so you don't have to randomly scribble like crazy right now, but this gives you a feel. So just in the world of patterns for curation, I've listed about 8 blocks here, and there's another 15 blocks out there that have emerged even in the last month, right? Patterns for proofs of compute work. So there's human work and there's compute work, right? Within the world of compute, there's work around data and there's work around computation itself. So for data, Filecoin, for example, they have something called proof of space-time. Did you store this data for, say, 1 year in this location that you promised you would store? And if you moved it, if you stored it on S3 and grabbed it last minute, that's cheating. That doesn't work. So that's proof of space-time, right? A lighter version of that is proof of data availability, which is simply, did you serve the data up to someone when you were asked, right? And that's all that's needed in some cases, right? There's other things there too. Proof of replication. Did you have 5 copies of the data spread around in various places? And then on the computation side too, you have non-interactive proofs, interactive proofs, and subsets of that are things like zero knowledge, snarks and starks and all this, or something like homomorphic encryption, which is actually compute on encrypted data, which is kind of amazing that it even works, right? Like you can literally take data, encrypt it, and then take another data set, encrypt it, and you can add them together, even though it's encrypted. And you can multiply and stuff like that. So you can actually have privacy-preserving compute. That's one way to do it. You can also do things like multi-party compute, where one party does a tiny bit of computation on plain text data, another party does another tiny piece, and then it all gets merged together after the fact. And 3-4 years ago, so a lot of these theories have been around for decades. But in the last 2 or 3 years, this stuff got practical, actually. Practical enough to run and put into production systems. So Zcash is probably the best example of this running, where it went live, I think about 2 years ago now, almost 2 years ago. And it's actually using zero-knowledge proofs so that when I send a transaction from myself to one of you, the miners actually don't know how much was in my wallet when I sent it, right? And that's very, very useful. And there's more of these coming along too. You might have heard about Intel SGX. That's an example of a secure enclave, where basically Intel is saying, if you trust us, which is a big if you trust us, then as a hardware manufacturer, then we won't be able to see what's going on inside this chip in your computer, right? So these are examples of patterns, and overall, there's all these patterns. I just gave some examples for curation and the proofs of compute work, right? And in the proofs of human work, there's things too, right? I mentioned, the Steemit case, the Augur case, and so on. That's funny. That's all good. So all good. Yeah. So now I'm going to do 2 case studies. I'm going to do an analysis case study, and then I'm going to do a synthesis case study, a design one, on Bitcoin and Ocean, respectively. Okay. So. And I'm just going to be pretty quick about Bitcoin, but we're all familiar with Bitcoin and love to look at all the analyses. And in this case, I'm going to talk about the objective function of Bitcoin. And really, if you look at the heart of Bitcoin, if you look at its block rewards function and kind of reverse engineer and go backwards, what it's trying to do is maximize the security of its network. It defines security in a very specific way, and that is compute power. The difficulty in rolling back changes to its transaction log. So Bitcoin, first and foremost, is trying to prevent people from coming in and just messing with its transaction log, because if it has that log as transactions, nothing else matters. So if that gets compromised, everything else is gone. So how does it do that? This is what its block rewards function looks like. It's the expected value of its block rewards on the left are proportional to the hash power of the actors, which is the contribution to security, times the number of tokens at that time. So I will unpack this. So every 10 minutes, right now, a miner gives out 12.5 Bitcoins, okay? Or, sorry, receives 12.5 Bitcoins from the Bitcoin network. Which miner? Well, if I have 10% of hash power of the Bitcoin network, I have a 10% chance of getting that reward, right? So my expected reward every 10 minutes is 1.25 Bitcoin, right? It's lumpy, it's got high variance, right? Because I only get it 1 in every 10 times. But that's my expected value, right? If I want that lower variance, I would just go into a mining pool 1 level up, right? So there's a way to do that. And that's why I say on the left, I've got this expected value of block rewards. It's proportional to my hash power, in my case 10%. And then this T is basically 12.5 Bitcoins right now, right? And every 4 years that divides by 2, right? So it's went through 2 halvings already, right? It started off at 50, then went to 25, now it's at 12.5, right? And 100 years from now, it'll be basically nothing, right? So that's Bitcoin's objective function. It's very, very simple at the heart, right? But from this, everything else has emerged, and I'll get into that actually. How well did this work as an incentive? Well, basically remember, it comes down to maximizing security, which means maximizing hash rate. If you assume ASICs, and all the modern miners have a state-of-the-art ASIC manufactured on either TSMC 8 nanometers or 11 nanometers, and they have these giant mining farms, right? And Bitmain, by the way, is kind of starting to run ahead because they've got even better chip designs than everyone. And but basically, it comes down to then, assuming ASICs on modern everything, then it comes down to maximizing electricity. It's working so well on this that Bitcoin is already using more power than most small countries, and it's going to use more power than all of USA by mid-2019. It's increasing 20% per month, right? And you might think, oh my God, that's terrible. And actually, I agree, that's actually pretty terrible for the environment. And there's a lot of other more energy efficient Bitcoin blockchain consensus designs and so on, right? But my point here is, holy cow, is this powerful in terms of incentives, right? So we've got this very, very, very simple block reward at the heart of this whole system. We've got some software running, and it got people to run around and create massive mining farms like this to go and spend hundreds of millions of dollars to build and manufacture these chips. And this whole industry has come up around it, right? Miners here and mining pools and wallets and sparking the whole blockchain revolution from that very, very, very simple token reward function, right? Blockchains are incentive machines, and Bitcoin is the best example, right? But the cool thing is, it doesn't stop at Bitcoin. That's just the start, right? Which leads me to Ocean, right? So realizing that the superpower of blockchains is incentive machines, realizing that the future of society will be very dark indeed if we end up with data silos by a small handful of super powerful organizations. Realizing these things, we, as a team of Ocean, we said, we're going to try to do something about this. Just a small handful of people can't do much on their own, but we can create a network that incentivizes the world to work together to basically democratize data, make it available to everyone, have a data commons, have a data marketplace, as well as protect personal privacy, self-sovereign data, all of that. So what does Ocean look like? Well, of course, I showed you the slides at the beginning where we were flailing, and we went through that for 2 or 3 months, right? Sort of like that, first year PhD student playing with algorithms and stuff without realizing that maybe there's a methodology. But then we wrote down these objectives, we asked what we wanted, and so on, and went with that. And in the end, we got something we're pretty proud of. So first step we did was asked, who are the stakeholders, right? We actually came up with about 15 of them. And from that, we distilled into the 5 that you see here that are the ones that the network itself interacts with. There's others around, like regulators and stuff, but these are really the key ones. What are they? It's the people supplying the data. It's the people using the data. It's the people in between, which is basically the curators and the marketplaces. It's the verifiers of the data to make sure that it's good, that the people supplying the data aren't lying. And finally, it's the miners or the keepers, right? That's the core actors in the Ocean ecosystem. With each of them, so I list these actors on the left. With each of them, we listed the gives and the gets, the possible gives and the gets. So for example, the data providers, what value they provide? Well, they're giving the data, or the data availability as a service is a better way to put it, right? What might they get in return? Well, probably tokens for making the data available, right? Providing the service. And ideally, they even get rewarded even if the data is free, right? So you have to kind of reconcile this problem of, data wants to be free, and it also wants to be expensive. How do you reconcile that, right? Well, blockchains are actually pointing to a new possible solution. So the free part relates to the physics of bits, right? You can copy bits. The expensive part usually relates to compensation of the owners of the data, the creators, right? And the traditional way is, well, pony up some US dollars or euros and give that. But there's a new potential answer, and that is use the magic internet money that is being emitted from this blockchain, right? And that's actually pretty interesting. So anyway, going back here, we have these stakeholders, their gives and their gets. We took that and we said, we wrote down a bunch of things that they might want to be optimizing for. We brainstormed. We had 10 or 20 possible objective functions. And after some iterations on that, we distilled it into a key one, which was maximize the supply of relevant data. So why supply? Well, it could be, because maybe it's the consumer side. So why are we going for that? Well, in the case of AI, someone building an AI system is happy to take all of the data they can get, right? Just give me the data, right? So there's no problem from the demand side. They'll just grab it and consume it, right? But on the supply side, that's where you actually have the bottleneck. So you really want to actually incentivize that side. You want to incentivize people who have their own personal data, who might consider selling some of it to parties that they might trust a little bit or get enough money for. If you do it right, you can even help to unlock data from enterprises that's just sitting there, right? And also data within, NGOs that's kind of sitting there that they could make available, but they just don't know how, even though maybe that's their mandate, and so on and so forth. So it's about the supply, and then of relevant data, right? Now, relevant here, that's a big question too. What does relevant mean? Roughly speaking, it means useful to AI people in some way, right? Who are trying to build these models. So let's just take that as a placeholder. I'll give you a better definition of relevant in a second. We take that objective function and we cast it directly as a block rewards function, okay? So we go from objective function on the top, maximize supply of relevant data, to token rewards if supply relevant data, right? So that actually becomes the block rewards function, right? And then, but then we still have to figure out what does relevant mean, right? And you can look around, if you're in the sort of data engineering, big data field, there's a bunch of measures of relevant there. If you're an information theorist, you can start to look at the measures there, like MDL and all this. And there's a bunch of fields that have something to say about what data is relevant or not, right? And everyone has a different opinion. But you know what matters? The market, right? Why don't we let the market decide? We let the crowd decide, but they put their money where their mouth is of what's valuable or not. So we have curation based on staking, okay? And I'll show how that manifests in a few slides, but it's basically a curation market, right? So that casts to supply data, we replace relevant with curate. So now you get token rewards if you supply data and curate it, okay? So supply, making it available, and curating, okay? So that was the objective function, but then we also have the constraints. And as we were going through the different stakeholders and so on, we wrote down dozens of pages of possible constraints and ideas and so on and so forth. And really there's a dance between possible designs. You write down some designs and you say, what am I trying to solve for here, right? And then you write that as a constraint. So we actually had dozens of pages, but it distilled into these 7 main ones, right? For price data, data that's being sold in a marketplace, do we have an incentive for those sellers to supply more data? Do we have an incentive for people to refer good data to others? Do we have an incentive to prevent spam, right? So we have that for price data, but we also want to incentivize the data commons. So do we have an incentive to supply more? Do we have an incentive to refer? And what about spam? And it's different, right? Because if I'm selling data, I'm incentivized to supply it because people might want to buy it, right? But if I am giving data away for free, am I going to be incentivized to give it away for free? Not by default, right? Maybe. So we have to think about both. The next one is actually really important too. Do we have a good way of engagement, right? What we don't want is 99.5% of the people in the system to be hodlers, right? And my favorite example of a system that's really working well this way is Numerai. Of the top 50 token holders, 67% of them engaged in the last auction, actually for in their case, they're doing basically a tokenized hedge fund, okay? So they actually have a really great engagement rate among their users. Whereas a lot of the ecosystems right now, they didn't do enough that way, like Ethereum, probably less than 1% of the Ether holders are actually building dApps, right? Or using dApps. They're just hodling right now, right? Ethereum actually recognizes this. So as they're working towards the proof of stake algorithm, Casper, they're gonna probably put in inflation. And they actually have this running on a testnet right now, and the inflation is something like 10% per week if you don't stake your Ether and run a node. So basically, if you don't want your Ethereum to have inflation, you actually have to run a node to help make things happen, right? And that's actually pretty cool. So they're basically giving this stick to you unless you actually are engaging in the ecosystem somehow, in their case, in helping to secure the network, right, and provide compute. So that's coming down the pipe for Ethereum. And so this is the thing we want here too. You can summarize it as, does the token give higher margin of value to users of the network versus external investors / hodlers, right? That's kind of a way of thinking about it, right? A couple other ones, are people incentivized to run the keepers themselves, right? The miners, et cetera. And finally, is it simple, right? Maybe we have some big complicated machine, but that actually exposes a bunch of security flaws. So there's a trade-off between simplicity and the rest of this stuff. And kind of related to simplicity is onboarding low friction. Is it easy for people to get started? That last one is more of a UX thing, but it's important to understand. We also brainstormed, and we actually had pages and pages and pages of attacks. And a lot of this was hanging with friends over drinks saying, okay, please attack Ocean, right? Or sending drafts to the white paper to friends saying, okay, how can you conceive of attacking this and stuff, right? And so we actually have pages and pages of this, and we grouped it in various ways, right? Yeah, anyway, lots and lots of that. So once we had the problem defined, the objectives and constraints, then we said, let's try some existing patterns, right? And of course, as good engineers, we said, what's the simplest thing that could possibly work, right? Or come up with a design that's as simple as possible, but no simpler, right? And it could possibly work, but it might mean that maybe it fails, and it probably will. So, well, an actor registry is pretty simple, right? It's just a registry of the good actors. So that's a simple one. Or what about a registry of just the data? That's useful, right? Or what about a registry for each, actors and data? Or maybe the fourth one is starting to add in some curation on the data, okay, a curation market. So those are 4 pretty simple designs, the first 2 especially. How do they do? So this is a key thing here. So remember these key constraints we had before, the checklist of 7 things? They're here now, right? Now we have these 4 designs, and we said for each of these designs, how does it do on these constraints, right? And now this is sort of the heart of the methodology in action, right? So we say for design number 1, which is the TCR of actors, the registry of good actors, how good is it for priced data at incentivizing supplying more? Well, it doesn't actually have anything on there because it's just a TCR for good actors, right? Now they're kind of, I guess, incentivized to supply because they want to make money just selling and the price data. But it definitely doesn't have anything for free data, right? There's absolutely no incentive for these actors to put in free data. And also, it does pretty bad in spam prevention. It fails in a couple other things too. The second one, a registry for data, it fails in other ways, right? The third one, a registry for both, it fails in a couple things. For example, it has no incentive at all for referring, right? And to us, we see that as a really key thing for virality, for growing the network, and so on, right? And the fourth one, where you start to add in a curation market on the data, a simple one, it starts to stall, but it's missing a couple things there. So, well, we said, I guess we have to resort to a new design, and so be it. And by the way, I will mention, designs we've done since. It's been such a great moment where you're iterating with people and you try a simple design and you're like, it works, it solves the problems. So one organization we're iterating with recently, we got away with having just a curation market with a tweaked onboarding mechanic. And that's it. And we were so happy about that, right? So we added a couple things here, which are basically curation markets on the data with a work component attached. So basically, I'll get into what that means later, but it's basically a curation market with a bit of work. So how do those do in their 2 variants? Variant 5 didn't quite work, but variant 6 did. And this is critical. So when we hit variant 6, we're like, it hit these constraints. This means we can start thinking about stopping. And what we did then was, after we hit these, we went through this other big list of constraints and are like, does it hit here? This? Does it hit this? Does it hit this? In this case, it did. And we said, great, that's our stake in the ground for the design now. Now we can proceed and flesh out the white paper, et cetera, et cetera. It's not saying that the design is perfect for sure. And in fact, as we iterate and build the system out, we're seeing we can make a tweak here and make a tweak there. And we continue to verify and so on. And maybe even after that, the design will be maybe a lot different by the time the network ships and stuff, right? Or later on. But at least we knew we could stop then with the information that we had, right? So this is really key. This was kind of a magical moment. You knew you had your design of when to stop. And when you come up with a design that met those constraints, great, you can basically stop. Also, the other part besides the constraints is how well does this thing do on the objective function? What is the objective function? Notice I framed it to look as close as possible to Bitcoin because, well, that's a really great design. So if you can have something that has a similar shape to Bitcoin, that's a great start, right? But obviously, there's other networks out there that are doing well too. And so having a pattern that looks close to an existing pattern, that's really useful. So in our case, we were actually starting with, we're trying to have this pattern of work. Remember, we reward curating the data by staking on it and making it available. So serving up data when asked, okay? What does that look like? And by the way, we call that a proofed curation market. So it's a curation market with a proof of work attached, where the work is making data available. So the expected reward is a combination of two things. The predicted popularity, so that's your stake in the popularity of a data set, and the actual popularity, right? And then the token rewards in a given interval that's given out by the network, right? And this is the expected reward for a particular user serving up a particular data set, right? And it's all normalized and stuff too. And there's a couple other tweaks here. Notice that there's a log on each. The log actually helps to mitigate the effect of stake whales. What if someone has a ton of stake and they just start to dominate? Then it helps to mitigate their effect. Or what if you have one super popular data set and it ends up getting 99% of the block rewards, right? So by having the log on that, what it does is it encourages a diversity of data sets. Also, it turns out that the log, those of you who are economists, it actually relates to the Kelly criterion, where the delta in utility that a user sees is actually not based in the absolute change, it's actually based on the log of the change, right? So we've actually got the log of the change here and the wealth that comes to the miner, right? It's also broadly used in AI. So in the world of AI, we use log all the time as well because it softens the effects of basically scaling. So it allows you to basically converge more robustly. It's a very common trick. So this is basically the predicted popularity, the actual popularity bound together, right? One of the things we realized though was we had a constraint in there, and that was, are we handling privacy well enough, right? And so we had that constraint, and we also had another constraint of, for really big data sets, let's say you've got 1 petabyte, it might be where you really don't want to move that across the wire, across the net to someone else. It makes so much more sense to have compute locally where that data is sitting, right? The really, really heavy data, right? A third thing that was happening was there was emerging decentralized AI compute and just decentralized compute. Things like Golem Network, iExec for generalized compute, privacy-preserving compute like Enigma, as well as AI compute like SingularityNet. So we've been asking, how do we link those in? How do we link those in, right? And we realized all of these we could actually handle very straightforwardly by simply tweaking this. Instead of the predicted popularity and actual popularity of making data available as a service, it can be a more broad service. It can be a service of data availability or compute, right? And so that's what we have. And basically then overall, Ocean is actually maximizing a supply of relevant services, right? And generally it's data availability as well as compute services. It actually can be more broad, but we're focusing on that for AI, right? So that's what Ocean is about. It's actually this network for AI services. And you can frame it from a pure AI perspective. So for example, in the world of AI, there's this, if you rewind 10 years, Google came up with this thing called MapReduce, which was about doing massive compute across 1,000 or 10,000 machines at once. And that was ported to the open source world via something called Hadoop. And Hadoop was a bit hard to use, so more recently something came out of Berkeley called Spark. And Spark is a very, very popular tool for basically doing distributed computing, not decentralized, just distributed computing for AI jobs, right? And think of Ocean then as decentralized Spark. So, or a compute pipeline for AI where it does job A, then job B, then job C, then job D, storing data along the way. So there's a few ways to frame Ocean. Overall, it's really this network that is about enabling AI compute, focusing very much on curated proofs of work. So this is the experience in Ocean, and as you see, it actually met these constraints. I'm going to talk a bit now about some of the things we saw were lacking as we were going along. We saw that there was a methodology kind of missing. So we worked on a methodology. It worked for us. Since that time, we've actually helped. I've probably helped about 5 or 6 projects myself. I've had other friends use this, and it's worked for them too. And it's worked out pretty well, but I'm not saying it's a panacea. It's just another tool. But what about software tools? And I want to talk about that briefly. So throughout the 2000s, I spent most of my sort of AI career in the world of circuit design. If you're a designer for Intel or Sony or Apple, you sit down and design, you sit in front of your computer on a given day, and you're designing a chip, right? Inside your iPhone, you've maybe got 15 chips. And those get designed by engineers in Silicon Valley or wherever, designing these chips. And the thing is, when you design this chip, you maybe have a team of 10 or 30 engineers. They work together for, say, 3 months, and they get this chip manufactured. These days, to manufacture one chip costs $50 to $100 million because the masks are so expensive. That's just how it works. And it's on a foundry that actually costs $5 billion to build. So there's only 4 companies in the world that have world-class foundries. You've got Intel and Samsung, you've got TSMC, and the up-and-coming one is the one from China called SMIC. There's some smaller ones, but they don't really matter. So there's just a small handful of companies, and it's really expensive. So when you design that chip, because it's costing $50 million to deploy, you better get it right. Well, guess what? This industry has emerged for software for designing computer chips. It's been around since the early 80s. It's called the EDA industry, Electronic Design Automation. It's about a $6 billion industry. It's actually laughably small compared to the $400 billion semiconductor industry. But the semi industry really relies on it. And what this EDA industry does is it actually builds CAD tools for simulation, verification, and design of chips. And I'm going to give an example from each of those. Okay. So for simulation of circuit dynamics, this is an example. On the top left, we have a drawing of a circuit with some inductors and some diodes and transistors. And then basically it runs through the simulator, which at the core, it's basically a set of differential equations, usually ordinary differential equations. And it's solving those using optimizers, et cetera. And it's based on something called SPICE, which came out of Berkeley in the early 70s. And there's all these derivatives now, mostly called things like HSPICE and PSPICE and all this. Sometimes people get creative and don't actually have the word SPICE in it, like the name Spectre, it's another simulator. And once you run that simulator, it gives you different results in the form of data points, waveforms. And you can do different analyses. You can do a sort of a steady state analysis, DC, frequency analysis, all of these. And that's what these are here for various things. So this is a time series analysis over time. This is a frequency analysis and so on, right? And this is something that has emerged over the years. The reason there's different analyses, it's because you want to look at the circuit from various angles, right? So you have these simulators. They're a standard. They're a key to the design of these chips that we all rely on. Once you have a simulator, then what you can do is you can wrap it with another CAD tool on top that verifies that that design is going to work. For example, if you have a chip that you want to make sure that it works from -40, like we get in Canada sometimes, -40 Celsius or Fahrenheit, it's the same thing there actually, all the way up to say +40, and also maybe from a power supply of say 1.2 volts down to 0.8 volts, and maybe some other variations. How do you make sure it's going to work across all those possible combinations in a continuous valued sense, right? Well, there's tools for that, right? And here's a tool for that, actually, that I helped to develop throughout the late 2000s called FastPVT. And it's used by NVIDIA and Qualcomm and all these guys. And it's really a tool to help verify that your circuit is going to work, right? And this is just a standard practice in these companies to basically make sure that these chips work, such that when you commit to your $50 million to manufacture the thing, you're not going to screw up, right? There's this idea of one spin silicon, first time silicon success, all that. And then finally, once you have really good simulators, once you have really good verification, you can start to have design, you can start to have interaction with the simulator across worst case conditions to try to explore your design space more readily. So going back to the example of a car design, right? You can say, okay, we've got different diameters of the wheels, we've got different sizes of the engine, right? What about the interactions of those? Maybe it's not linear. So maybe as I change the diameter of the car, and the size of the engine at the same time, maybe the top speed goes up quadratically or something, right? And so that's what this is showing here on the top right. It's showing actually a nonlinear interaction between two variables, right? And the z-axis is some output. And if it was a linear interaction, so this one here, you can see that it's only dependent on one variable, this one here. It's not dependent on the other one at all, right? So you can have these tools that have interactive design where you can actually move around the design in two-dimensional space or higher and actually see the effect in real time, right? And this is actually now becoming a standard in the circuit industry. So the summary is that there's really good tools that basically power the chip industry, which in turn powers all the electronics around us, from this projector here to this laptop to all of your cell phones to these lights, et cetera, right? These lights are probably IoT by now, right? So they're going to get hacked and we're all going to be in the dark. Yeah. Hopefully not. But anyway, that's kind of the summary. So how are we doing for tokenized ecosystems, right? Are there tools for simulation? Nope. Actually, there's one that just emerged called Incentive AI. You'll hear more about it. It's just emerging now. Are there tools for verification? Nope. Tools for design? Not at all, right? We need the other ones first for that. So we have these tokenized ecosystems to design, right? The total value is what, 200 billion, 500 billion? Who knows these days, but it's a lot, right? It's, 10 times, 50 times bigger than the EDA industry, yet we don't have tools at all, right? There's, you deploy one network and it could turn into $1 billion network in under a year, right? Or right away sometimes. So we're designing these massively important, massively, with lots of money flowing around without any tools. We're basically flying blind, right? We could be getting it all wrong, really, right? It's super scary. And for myself, from coming from circuit land, used to these tools over time, I'm like, I need these tools, please. So I'm running around trying to convince everyone. And I don't have any slides for it, but there's something that goes hand in hand with this sort of practice I mentioned in the tools, and that's theory. I guess I'll mention later. Can we have better theory around this? And cryptoeconomics, of course, plays a key role here. And the fields that led into it, things like mechanism design, game theory, all of this, right? And there's now starting to be some papers that are emerging. So for example, Michael Zargham presented a few weeks ago a paper where he said, let's have a model of all the possible actions of agents running around, of miners. And if we have the mathematical model, then we can actually choose what actions they have. And then we have this overall space, a state space of all the possible things. And it doesn't matter what people do. You know that the actors are going to run around in the state space. And then what you can do is say, what's the worst case conditions in the state space, right? And that's a great example of basically applying this tool here, across all possible conditions. Is your tokenized ecosystem going to work okay? So we're starting to get there with the right combination of theory and practice and tools. So I'm going to wrap this talk up quickly here towards token engineering, right? And so, if you actually, just to take a step back, right? If you ask an economist what's the most important field for crypto, for sort of this world of blockchain, they'll say economics, right? If you ask a professional cryptographer, they'll say cryptography, right? If you ask a game designer, they'll say game design, right? So everyone wants to think. If you ask a lawyer, they'll say, oh, it's the legals for sure, right? If you ask a regulator, they'll say, oh, the regulations, right? So et cetera, et cetera. So everyone wants to claim their field as their own. And the honest truth is all these fields are important, right? And this is really truly a new field, right? In two ways, from the sort of science side as well as from the engineering side, right? And the cool thing is, if you're coming from one of these fields and many other fields too, whether it's electrical engineering or physics or public policy design, everyone has something to contribute, right? They all have their own expertise to draw on, and if we actually work together and teach each other these things, we can make this field really amazing, right? Rather than saying, okay, it's only the economists that can do this, right? Instead, it can be everybody drawing on their knowledge, making something better for the science and for the engineering. So here's some of the fields and how they relate. Sort of analysis of these systems, you could argue that game theory is maybe one of the best fields for that. There's also obviously other fields. And then for synthesis, the sort of analogy of game theory is mechanism design, right? And there's some really, really cool theories in mechanism design from which like Nobel Prizes were awarded in the mid-2000s even, right? And you can actually take mechanism design and kind of constrain it, add a few constraints to it, and you actually end up with optimization design, which is really cool, what I talked about earlier. So there's a direct link from mechanism design to optimization design, right? But then from that, if you have just saying optimization design, it's sort of this, a set of a few rules, it's not quite its own real field, right? But what if we actually said, you know what? We need the theory, we need the practice, going hand in hand, we need the tools, and we also need the responsibility that comes, especially with engineering, a lot of other fields, but trained as an engineer, you're kind of instilled with a sense of ethics of being responsible for the designs that you build, that you deploy, and so on, right? So these things coming together, theory, practice, tools, and responsibility, this is really the realm of engineering, right? And so about, 6 weeks ago, I was trying to use different words for all this, and I realized, I'm going to, call a horse and a cat, and I'm going to call token engineering, right? And I just decided that would how it would be, and I ran it past some friends. What do you think? And it seems to be sticking. And the idea is it's an engineering field. You could call it behavioral engineering or incentive engineering and so on. But if you think of what's electrical engineering, that's really electrons flowing around, right? That is the substrate for electrical engineers to design. What's mechanical engineering? It's really mechanics as the substrate, right? So what's token engineering? It's tokens as the substrate for this new engineering practice, right? So that's kind of the root of that idea. And of course, it goes side by side with token economics, tokenomics, cryptoeconomics, right? So engineering, just going back, it's the creative application of science, mathematical methods, and empirical evidence. By the way, this is from Wikipedia, so I'm just reading out loud, right? It's, so application of these things, using science and other things to innovation, design, construction, operation, and maintenance. So it's not just, that first innovation step, it's the whole life cycle of whatever you're building, right? To a whole bunch of different substrates, right? Structures, machines, materials, devices, systems, processes, and even organizations, right? And there's this sense of responsibility. I mentioned this briefly, but a bit of a story. In 1994, it was my first year undergrad engineering, September 1994, so now you know how old I am, or roughly. Within that first week, we were shown a video by one of our professors, and it was actually of the Tokenize bridge collapsing, right? And on it, actually, no one died. No people died. Actually, a couple dogs died, I think. Fortunately, they got lucky. But what happened was the engineers failed to account for resonance. So basically, as wind came along, it started resonating. And the amplitude of the sine wave of the bridge going like this got higher and higher and higher from the interaction with the wind. And that wasn't part of the models at all. And so there's a remarkable video showing this, how this bridge went higher and higher amplitude until it collapsed, right? And, but the engineers, they should have known better, right? They know about wind, right? So they could have modeled this, and they didn't, right? So we were shown this video several times throughout my undergrad career. And if you're a Canadian engineer like myself, you have this ceremony at the very end called the Iron Ring ceremony. And in it, you get this iron ring, and the rest of it is super secret. And we have to tell people, no, we do not kill goats, and we really don't. But the rest of it's secret. And but we get these iron rings, and the myth is that these rings are from a collapsed bridge somewhere in Canada. Maybe not Tokenize, because that's in USA, but some bridge. But and I wore that ring for years and years and years, actually, as a reminder to myself about responsibility and so on. And the only reason I don't wear rings now is because I've gotten old and my finger got fat, basically. So what can I say? But overall, as an engineer, you really get this drilled into you. But of course, this is not the realm of just engineers trained as engineers. This is the realm of everyone building these tokenized ecosystems, right? A sense of responsibility, a sense of ethics, right? And it's really important to not forget that, right? So engineering has theory, practice, tools, and responsibility, right? And there's lots of engineering fields that go back more than 100 years, right? And the relationship between science and engineering, engineering, the KPI, it's about building things that work. Whereas science, it's about contributing new knowledge, right? They go hand in hand, they're complementary, right? So token engineering is complementary to the science of cryptoeconomics and token economics. That's kind of how I see things. Everyone can define this their own way, that's cool, but this is kind of, how I see it. So this is sort of like my framing of sort of token engineering. And after I first gave this talk at ETHCC, where I met Sandra, about 6 weeks ago now, I think, it was really remarkable. A lot of people started coming to me and saying, hey, this is really cool. How do I get involved? And so on. How can I contribute? And so a lot of people reached out. I had a lot of great conversations. And we started to realize, including Sandra, part of the reason I'm here today is we need to share knowledge, right? To learn from each other. Like I was talking about before, there's a bunch of experts at different things. We're all kind of here because we have a bit of polymath in each of us. We want to jump disciplines, to form new disciplines, to connect dots, right? And to learn from each other, right? And so within the context of token engineering, there was an opportunity to do something there, right? So as we were starting to sort of think about how to move this forward, and I was, also myself and friends, we were talking about things like Peter Hinchins with the C4 process and, growing other online communities. So the mission, one way to frame it is to grow token engineering into an engineering discipline. I think no one is claiming that it is one yet, but we can go that direction collectively as a community, right? But of course, with the ideals of the decentralized world. So decentralized, permissionless, open source, that all can contribute to and all can use, right? That has to be manifested into the blood, right? There can't be sort of some centralized authority saying, this is how token engineering works, because that's completely against the ideals of blockchain, right? So, and what's cool, actually, there's a really great inspiration that goes from one of the more recent engineering disciplines of software engineering. So for years and years, people were hacking and hacking, but software engineering really came into its own in the mid-90s and early 2000s. And it emerged really from the C2 wiki, right? People like Martin Fowler, Eric Gamm, and others. So they created this wiki. One of them literally invented the wiki, the idea of a wiki, and then they started populating it immediately with patterns they were seeing in software, right? Software patterns, and you can see that on the left. And as these patterns got fleshed out and discussed more and more, and people contributed together, Wikipedia style, before Wikipedia, of course, it emerged into a book, Design Patterns, right? By the Gang of Four. It's one of the most famous books in software engineering. But it wasn't just one book. This group of people that kept growing as a community started writing other books, like refactoring. They wrote books about UML, so giving more process to higher level software, so you can have UML as a visual language to quickly grok and understand design patterns, right? And link them together into higher and higher constructs. And then they also started realizing, hey, with this new sort of software engineering approaches, we don't have to go back to sort of this old school waterfall method. When you refactor, you can actually change the machine as you go, right? That's very different than sort of changing a bridge 10 years later. You can't really massively refactor a bridge, but you can do that with software, right? And you can iteratively improve, and that's where the agile movement grew out of. So all of this actually came from basically the growth of the sort of software engineering community, the wiki, everything around that. So we have a really wonderful template that's pretty recent for engineering itself, right? In this case, software engineering. And there's other great examples too, right? A lot of different open source movements out there, right? One of my favorites is ZeroMQ, which basically developed and fleshed out the C4 process. So if you like XP or if you like Scrum, really look at C4, it takes things to the next level. So what that means then is, why not start with a wiki, right? So we've actually put up this wiki called tokenengineering.net. And it's actually got 4 key components in there right now, sort of as a skeleton, and that's building blocks, tools, reading resources, and community. And I'll talk about each here and then kind of show you guys. So here's some building blocks. You know the slides before, I showed you a bunch of curation building blocks. Well, it's got there, and proofs, identity, markets. And by the way, see how this list is a bit different? You know why? Because I just wrote down a list of 5 or 6 things to start with, and the community has gone in there and added new things and changed things around and so on, which is awesome. That's exactly what should be happening. And remember, this is a wiki, right? So anyone can go in, they click edit on the bottom. If they don't have an account yet, they sign up in like 1 minute, right? All it asks for is your private key of your Bitcoin address. No, joking. No, of course, just your email. And then you go in, and then you start changing things, right? And then you can drill into the curation part. And so there's a bit of a roadmap not a roadmap, just a framing of how these different curation things relate. And then you can even drill into each of the different building blocks, like the TCR. So this morning I got in a bit of a roll, and I decided to flesh out the TCR page. So the TCR now has its own wiki page. Describing things, and you can go in there and change things and add things and so on. And actually, it's kind of amazing. TCRs themselves have undergone an explosion in the last 2 months. There's some people like Matt Lockyer and others that have just been kind of going crazy in a really great way with TCRs and building on other things. So I encourage all of you to go in there and add building blocks and ideas. And of course, it's not just the building blocks, but also the tools, right? So what about the tools for simulation and verification and design, right? Well, I mentioned Incentive AI. Well, now there's a link. Someone else has actually put in a case of partial slashing simulation, an agent-based thing. If any of you are working on agent-based simulators, and I know at least one of you is, great. Please put it up here.
We have an event.
Oh, there we go. Awesome. So there we go. So I encourage all of you guys. This is the collective place for the world to put the stuff in a permissionless, open source way, right? There's related disciplines, so it has links to that if you want to learn. There's also some articles that all kind of came around the same time that sort of gave the idea of token engineering from various angles. Everything from Alex Evans on sort of a crash course in mechanism design. And that's actually really showing how you go from mechanism design to optimization design. Or Michael Zargham has written on engineering economic systems. I wrote a couple of blog posts on this, and there's a few others, right? And that's just kind of a starting point, but of course the other places drill in as well. There's also, in the last 6 weeks, the community has been growing. we actually have had a couple workshops in Berlin around the Berlin meetup. Then there was a workshop in New York, sort of a global gathering of a bunch of people from all around, right around this time of consensus. Following that, in ETH Buenos Aires, there was another global gathering. And now there's actually 6 meetup groups that have emerged. So there's one in Munich, there's one in Toronto, there's one in London, there's one in Zurich /Zug, and one in Tokyo. So if you guys are interested in, even framing this as a token engineering meetup, awesome. Or collaborate any other way, however you want to do it, right? And now I'm seeing every few days people like say on Twitter, hey, I'm starting a meetup here, and they CC me. I'm like, great. They're like, can I do it? I'm like, yes. You can't ask me permission because I can't give you. It's you, right? So which is wonderful, right? And to give we have some list of events, other meetups, and by the way, see here. Related meetups, cryptoeconomics.hub Madrid, right? We've actually also got a link to the Telegram channel. So there we go. So I encourage you guys to put other links here and stuff too, right? To sort of have this community that's trying to share knowledge and learn together, right? And of course, there's ways to participate. You can edit the wiki. If you're on Twitter, tweet with the hashtag. There is an account for token engineering, but of course that has control by one person right now. So, and which is too bad. So right now that's just basically the people doing the newsletter to help people know about the newsletter. But the 2 main things are editing the wiki and the token engineering, and of course attending meetups and starting your own, right? And there's a mailing list here too. And the people on this GitHub, this wiki, there's already been dozens of people contributing in the last few weeks, which is great. Here's some of the people following. And so I will conclude. So I've talked about moving towards this practice of token engineering with this realization that token design is a lot like optimization design, which is great news because we can approach token design as optimization design. Formulate the problem, try existing patterns, iterate as needed, and only if needed to try a new design, right? This helped a lot for us with Ocean, as well as for some other designs. And it's led us towards realizing that we really can aspire towards this new engineering field of token engineering, which combines theory, practice, tools, and most importantly, responsibility. And a community is forming, right? So tokenengineering.net, hashtag token engineering, all of that. So I will stop there, open the floor to questions. Thank you. Yes?
I have a question. You mentioned that Ocean Protocol is the network for AI services.
Yeah.
But I conceive them more as like a platform for selling data and connected with AI. And it really shocked me that you say that. Because then, do you really compete against SingularityNet?
No.
Because their mindset is similar. Like they want to do this blockchain where AI pay for the services and connect them all together.
Yeah. So Ben, the founder of SingularityNet, he's a friend for like 10 years. We both come from the AI community, especially the crazy AI stuff like the artificial life and evolutionary computation and stuff, right? So, I'm officially an advisor to SingularityNet, and Ben is officially an advisor to Ocean. So we have aligned our incentives basically, right? And overall, so first and foremost, Ocean is about data, but we realized to solve some of the data stuff, we needed to make it really easy to plug in compute. So there is compute stuff. We are supporting compute services, and that's where SingularityNet plugs in, right? So SingularityNet services for building models, et cetera, plugs into Ocean. On a vice versa as well, though, Ocean itself could be supplying data to SingularityNet, right? So you can actually frame it both ways, and both are valid, right? So we're not trying to have one above the other. They actually play with each other as basically siblings, right? And we have excellent relations with them, et cetera, yeah. And this is similar with a lot of these other things too. So Ocean itself, it's not a data marketplace. It's helping to power data marketplaces. So a good example is, think about if you go onto kayak.com, you want to buy a flight, a plane ticket. You do a search for, say, Berlin to Madrid, or of course from here, Madrid to Berlin. One way, of course, right? Yeah, joking. But you want to check out room 77 in Berlin, of course. So you want to buy a flight, and you see that there's flights from many different airlines at once, right? And each airline has actually populated a database. This database is called Sabre/Amadeus. They're kind of merged, and you can go to Kayak and see this. But you can also go to Travelocity. You can also go to Hipmunk or Trivago, and all of these are basically marketplaces for the same underlying data set, a substrate of the flights that are available. It has flights, it has hotels, right? So that's actually really wonderful because we see innovation at the experience of the users, right? There isn't, there's this sort of agreed upon underlying database that everyone's using, right? Which is actually generally really good for the user, and you can have this flowering of marketplaces like Hipmunk is very different than Kayak, is very different than Trivago. Compare that to music, where there is no underlying database. Instead, you've got Universal Music it's hoarding their data, and you've got Sony with theirs and so on, and they don't want to share. And in the end, we have 15 different streaming services that all look the same, right? And it's impossible to start your own new service, or it's really, really hard, right? Like SoundCloud basically has tried, and Spotify, but now it's just very hard to have anything unique and interesting because they're all trying to just gather that data. They're fighting at that lower level. So Ocean is basically trying to do like Sabre for airline flights, but for data itself, right? So not just flights, but sort of for everything in a way that no one owns or controls that lower level to unlock the Kayaks and the Trivagos of the world, but not just for flights and so on, but for data marketplaces. And maybe there will be some for self-driving car data, right? We're part of a consortium, including Toyota and GM and so on, for self-driving cars. So that's a real one. Or for health data. And for each of those, there could be 5 or 10 or 20 different marketplaces. And Ocean can be helping to supply data for all of them, right? So that's how Ocean helps to supply the data marketplaces, as well as there's interfaces that will emerge for data commons, right? Free data that's just put out there by NGOs. Right now, there's actually a lot of open data sitting around in silos, because the people with their open data, whether it's OpenML datasets, which has like 20,000 datasets, or OpenStreetMaps and all these others, they're sitting in 1,000 different silos in the web, and they're not incentivized to put them into one place. But if you have tokens to incentivize people to put them in, then you into one substrate that is not controlled by anyone, but it's more a public utility for everyone, then it's actually a great benefit, and people can start focusing on the higher levels and have 10x or 1,000x more data for their AI models or whatever. So I hope that answers your question, as well as a more generalized idea of it. Yeah.
If the idea is to democratize data and remove silos, where do you see value added after, like in this scenario where everyone can access this democratized data?
Yeah, so there's it's one use case at a time. So the use case of self-driving cars, for example, the algorithms are there. Just like I showed this early plot, as you add more data, the accuracy goes up, right? So you could, if you actually had the algorithms of today, and you had 500 billion miles driven, then you would have accuracy good enough to ship the self-driving cars tomorrow. And that's a study that Rand did a few years ago, right? And actually, Toyota and GM and all these guys have realized this. And they've realized, oh, wow, if we're just going to do this on our own, it's going to be 15 years before we have the data. But if we all work together, then we can actually start to pool our data or buy it from each other in a marketplace, and then start shipping much, much sooner, right? So that's a great example, because it's a win-win. Not only it's useful for the car companies, of course, but also for humans for a lower accident rate. In US alone, there's at least hundreds of thousands of deaths per year. I forget the exact number, right? Also mobility, right? Right now it costs money to hop in a taxi or an Uber because the driver is getting paid. So imagine, and that's really hard for, say, an elderly person, et cetera, et cetera. So instead, if it's self-driving, then the costs will go down and you'll have much more mobility. And those jobs can be, people can get jobs elsewhere doing other things. So that's one. Another quick one is healthcare. So one project we're working with is on predicting Parkinson's. So the bigger the data set, the more accurate your prediction, or therefore the earlier your prediction, right? Parkinson's is a good example. Even better is cancer, where it's very well known that the earlier that you detect the cancer, the better your chance you have of stopping the cancer in its tracks, right? And if you're too late, then you're really too late. So that's another one. And there's a lot of other examples in like smart cities and space, and the list goes on. Yeah.
So if I understand correctly so far, the community itself has the responsibility to judge the quality of those data sets, right? Is there at any point objective measurement of the quality of those data sets? So is it only the intersubjectivity of the community, or at one point you do some kind of audit Or
So overall, the community judges on each thing in a curation market. So if I think that a data set is going to be relevant or popular, then I can stake on it. And I'm incentivized to stake on it earlier because I would get more rewards in a curation market setting. And then if others start to stake on it after me, then the value of my stake actually goes up too, right? And if I stake on it and I serve it up when asked, I get block rewards as well, right? So I'm incentivized. If I think a data set is useful, then I'm incentivized to stake on it and to serve it up. If I think that I have, if I want to make a lot of money doing Ocean, maybe I'm sort of like a day trader, but I'm really advanced with data science and stuff, right? Well, maybe I go in and I start building models of using these different measures of relevance that are out there with information theory and otherwise, and maybe those are signals to me where I can figure out which data sets could be really that other people find valuable quickly, right? Or maybe I'm just running an AI model, and every time a new data set comes out, I see how that data set helps improve my model. And as soon as I see that it's good, I stake on it. So maybe that's a good measure of relevance. But this is the funny thing, right? Everyone has a different opinion of that. So that's why leaving it to the market is actually a really pragmatic way to define it.
Is there some kind of feedback loop in terms of, so some AI service is using the data provided on Ocean protocol.
Yeah.
Is there a way for them to indicate back to the community after using those data that yes, indeed it was?
If they're economically incentivized, like if they want to earn tokens, then they will go and stake on it. If they build a model and they're like, oh wow, this data set really helped us, they will go and stake on the data set, right? And serve it up when asked, right? And of course, there can be counter games too. Maybe they go and they try to do head fakes to people and stake on data set that they think aren't useful. But we're assuming that the shilling point is towards the useful. If they want, they could write blog posts about how certain data sets are really awesome. Send other signals off chain. That's okay, right? And just like the data science community does that now. But what this does, it adds this extra dimension of literally economic skin in the game, right? So.
Maybe I didn't understand correctly.
Yeah.
So if I stake on a data set, what reward can I get in the future?
So if you stake on a data set, there's two ways you can get reward. One of them is if you say, I'm staking on it and I'm going to serve it up when asked, then when I serve it up when asked, then I can get block rewards, just like Bitcoin mining rewards, right? But it's Ocean mining rewards, right? So that's what a miner does in Ocean, is they serve up data sets when asked. And if there's 1,000 data sets, I don't have to serve up all 1,000. I can just stake and serve up one data set. So it's sort of sharded in that way, right? So that's one way I can do it. The other thing that I can do is the classic curation market setting where I can just stake on a data set. I don't have to serve it when asked. And then if other people stake after me, then the cost for people to stake on it will keep going up and up and up over time. And eventually, if I want, I can just sell it. So then my stake is worth more, and I sell it for more than I got it, right? So it's this early mover advantage, right? So and in both cases, basically those are signals to the market, and essentially the price of that token, that stake, is directly proportional to its popularity at stake, right? So another way of thinking about it, I'll get to, is it's sort of like a mini ICO for each data set, right? And in fact, curation markets have been viewed as another way to just sort of do fundraising for a project. Simon de Louvier calls it an arcade bazaar. So Ocean basically has it where with every single data set you have, you're actually launching a mini ICO, where you have this automated agent that's setting the price based on this curve. But once that curve gets far enough, maybe it's super liquid and there's 1,000 people buying and selling those tokens. Exchanges, if they want, they could list them, they can do whatever they want, right? And then you basically have this automated market participant. And so we have things like Banquo out there and other Uniswap, and they actually use this sort of automated market making mechanism. That's actually a subset of prediction markets. So it's kind of amazing that basically, sorry, not prediction markets, curation markets. So curation markets are actually automated market makers in their own particular way, a way to sort of do this mini ICO. But because of that, then the market essentially decides the value of that data set. And the related thing is, it's the value in terms of the stake in it, but people can still download it for free if they want, right? It can be the free if it's the commons, or it can be priced, right? So there's a lot of dynamics going on from some very, very simple primitives, right? Question?
Regarding the process, I don't understand why if you have some idea of a new pattern, why you don't try at the same time of the existing already patterns?
I don't follow your question.
I mean, you say only if there is not a pattern that it works.
Yeah.
You try a new one.
Yeah.
Why you don't try from the beginning all the ideas you can have?
So in general, because if something is untested, then it has a greater chance of failure. Like you can have something tried and tested and true, or something untested. So all else being equal, which would you use, right? One introduces a lot of risk. And in blockchain, it's actually really important because there's getting security really good is hard, right? And so if you can manage to say completely mimic, say, the Bitcoin blockchain, but swap out the proof of work with maybe proof of space-time and nothing else, then you've got a great system because you just fork Bitcoin, change one thing, and you've actually got a pretty secure system, right? Whereas if you completely design a new system and all this new code, then you could have 1,000 attack vectors and you have no idea. It'll take you a long time to fix that, right? So yeah, and this is actually related to this. This is the case anytime you have large engineering risk where it's hard to really predict well beforehand what's going on. So like designing aerospace systems, right? Or rockets, airplanes, they like to work with components that they know, and they like to only have small deltas in the design, because otherwise it's really, really hard. One case where they didn't do that, where they went top down from day one, was the shuttle. And that ended badly, basically, right? It was super unreliable, right? I think it was like 4% failure rate, right? Because we had, was it 2 or 3 explosions? Anyway, so bottom up with known components is a really better way to approach it from a risk perspective. Question?
I mean, I'm totally in this space and everything, but I actually have 2 big concerns.
Mm-hmm.
So one is, where do you see behavioral economics in all this? Because engineering is good for building bridges and software,
mm-hmm.
but we are here actually talking about humans and how we incentivize humans. And I mean, economic theory always ignored behavioral economics for a long time. And that's why we came up with all these theories that work well in the universities, but in the real world they doesn't.
Yeah.
So this is my first concern.
Could I answer that first? Because otherwise I'll forget. Okay. So I think actually, I know me. Does it have it here? No, it doesn't. So we really should add behavioral economics there. But overall, kind of, to go to another slide here quickly. Here, right here, right? So engineering is the creative application of science, et cetera, et cetera. So engineering takes in whatever knowledge it can take from whatever science is to learn, right? And I see the learnings from things like behavioral economics and all of these things can make a big, big difference, right? So towards, as an example, I talked about simulators, right? Simulating tokenized ecosystems. And I kind of have 2 views of this. One of them is, if you're building a simulator for circuits, it's a pretty closed system, right? And so you can get the dynamics pretty well. Although actually, believe it or not, it's really hard even to get the dynamics really well for circuits, especially when you have variation from manufacturing and stuff, right? So it's maybe you're like mostly trusting it, but not 100%. And that's even for something as simple as a circuit, right? But then, if you say you're designing a tokenized ecosystem, well, you've got all these miners, each with their own brain as humans. You've got, these messy humans in the loop, right? And then it's like, well, what are you going to do? Model every human brain or model a bunch of human brains? Can you get away with just agent-based simulation or something, right? Or some behavioral economics? The thing is, the agents themselves have to think of every possible conceivable way of attacking the system, right? So as a person, as a designer of that system, you have to think of all these things. So you can't just have a dynamical system simulator for these things. That's not going to work on its own. You need to, my first thought is you need to involve humans somehow, right? Or maybe use the dynamical system simulator to get that first 20%, sort of as a lint of like, okay, it completely sucks, so it fails this. And then from there, you need to have some sort of humans in loop, either with a bounty system. So imagine what you can do is you have bounty systems that get more and more and more value over time on the net until it gets to the time that you're going in the production net where it's the full bounty. A great example of a failure of that is EOS. So you've got this $5 billion network that the day before the network ships, they have only a $10,000 bounty for critical flaws. Like if I know of a critical flaw in EOS, I'm just going to wait one day and take $10 million or $1 billion from the network instead of 10,000, right? So they should have been ramping it up higher and higher and higher. An example of that, a better incentive is with Cosmos, where if you find a critical flaw in the Cosmos network, you get 5% of the tokens of the network, right? And that's a great incentive. So, and if you think about blockchains more broadly, they actually all have built-in bounty systems, right? If I find a critical flaw in Bitcoin tomorrow and can yank, 10% of the value from the Bitcoin network, which is whatever, $10 billion now or whatever, I could, right? And actually, according to the rules of Bitcoin, it's sort of a zero-sum game, and that's okay. But going back to your question, right? It's really hard to model humans' brains, right? Like no one has done it, and we can't. Like once we do, then everything else changes, and that's years, decades away, right? Right. Yeah. Exactly. So that's why you actually have to have humans in the loop to help model this. What we did with Ocean was we would send out the white paper, get people giving feedback. But as we move towards shipping the network, we're going to be doing more bounty things, right? There's another framing that I hinted at before, which was, this is sort of the direction that Michael Zargham is going, and he's saying, well, let's mathematically model all the possible actions that agents can have, and including all whatever range of emotions they do. If a miner can only do X and Y and Z, then if we have this sort of space of all possible states that the blockchain moves through, right, and it's bounded because we bounded what all the agents can do, and then we can shape that space based on different possible actions of the agents, then ideally we can bound it well enough that we get a useful design that's still safe. And then we can actually ignore actions and feelings and behavioral economics and all that, and just go pure math, pure dynamical systems. Now, I'm not sure how well that will work because it might lead to too much inflexibility, and we're starting to get there with that, and there's other people too. Just Zargham's probably the farthest along, and I see there's going to be sort of a back and forth. And if you really want a system that performs well, you're going to have to get into the messy human realm and kind of, this might be too constraining in the designs, right? It might be that the only design you have is like, people can go like this and nothing happens, right? So, although Zargham's gone farther than that now, to be fair to him. So yeah, that's my quick answer, is that like humans are messy. There's two paradigms around simulation. One absolutely needs to account for it, another one doesn't, but might lead to two inflexible design systems. You have a second question before, so yeah.
Yeah, okay. This is actually a thought I have in general. I mean, I can also ask all you this. Because sometimes I feel, you said this in the beginning of your talk, you said now we have incentives so we can make people do whatever we want.
No.
This sounds, to an extent, this sounds really creepy.
Yeah.
And I wonder if we not already live in a world where incentives messed up everything. So sometimes I feel, do we not actually need less incentives?
Yes.
This could all get totally wrong. So we could create a monster, like Bitcoin, in a sense, but in a total different direction.
Yes.
So how do you feel about this? Because in the end, I guess you and some of you at least want to make a better world.
Yes. So I have a few answers. Part of this is where the ethics and responsibility part comes in. We have to try. We have to try as hard as we can to have something that avoids these issues, right? We also have a get out of jail free card, which is called governance, right? So, hard forks is one extreme. The other extreme is on-chain governance with, things changing on the fly, like Decred and all these guys, right? And that actually allows you to change the dynamics on the fly if you see it going in the wrong direction, as long as the community of holders, et cetera, has enough of the values of the system itself. With Bitcoin, it's already been sort of captured by the miners. So, they're not incentivized to turn off the power, right? They're not incentivized to switch to like energy-friendly ASICs, right? So that's really a problem, and I've written about. I call it. Well, overall, there's this idea of a paperclip machine maximizer. An AI gone rogue that says, just maximize the number of paperclips. Here's the resources you need, and then it basically converts the whole world into a mound of paperclips, right? And so this is an idea that came out in the early 2000s. And we basically have something like that paperclip maximizer, that rogue AI, except it's a super stupid AI, and it's actually sucking the life force of the world, the energy of the world, and that thing is called Bitcoin, right? Now it's going to hit some maximum maybe, or maybe people are going to keep finding ways to like get more and more energy because it's profitable, right? So. Can we change Bitcoin? I don't know, right? But we can do our best, and we should do our best to design systems that don't cause these problems in the future. And by the way, there's other problems too. Like, if you look at the distribution of tokens of most of these other systems that have come out, it's a massive power law. There's like 5 people that hold like 80% of the tokens in a lot of these, right? Or, and it's kind of scary, like Stellar, it looks good across the board, except Stellar Foundation holds more than 50% of tokens. Same thing, Ripple Inc. holds most tokens, right? And that's the number 2 or 3 cryptocurrency. So they talk decentralized, but they're not quite decentralized yet, right? They're trying to get there, but like, guys, like, you gotta let go more, right? And because once you have the system there, like Brewster Kahle, he talks about locking the web open, and I think that's a really useful concept here too. It's really important to put these chains out where we lock the chain open and try to shift away from this sort of power law structure where you have this small oligarchy of players, and instead spreading the power as much as you can, spreading the value of tokens as much as you can, right? There's some other tools too. So there was one other thing here. What was I going to say? Oh yeah. So incentives. There's actually also a classification of extrinsic versus intrinsic incentives, right? So for example, if you're a teacher in a classroom, you shouldn't say, hey kids, if you study hard, I'm going to give you $1, right? Because then they're actually gaming themselves to just study hard or pass. Instead, what you want to try to do is give them help instill this sort of intrinsic incentives to learn and to grow and so on, right? So there's some things that you should actually not reward explicitly with tokens, right? And a great one in the world of blockchain is reputation, right? Like, if any of you is building a tokenized reputation system where reputation is tokens, please stop, really. It's super dangerous, right? Because people are going to be playing all these games, like, any of you who've watched the Black Mirror episode on that, or read Cory Doctorow's book on this tokenized system called Woofy, a novel from 10 years ago, you'll see how dark it is, right? And so, like, that's something where if you're doing reputation, you really need to move to implicit incentives. And there's related things too, like there's people trying to compensate creators of code on GitHub, right? But if you pay these creators directly, then it kind of removes like this sort of open source ethos, right? The good thing is the people who are trying, for example, OSCoin in Berlin, of course, they know this problem, and they're actually trying to approach it obliquely using curation markets and some other things, rather than directly on reputation. So basically, there's super dangerous things. We basically have an atom bomb that no one has really quite recognized that it's an atom bomb yet, right? And so, like, this is why I, once again, talk about engineering and responsibility, right? And trying to, like, raise awareness that this thing is way more powerful than we realize.
Or maybe we can even also start investigating about new types of incentives. I mean, if we just copy money, that's not really innovative. But if we say an incentive is you will be happier, I don't know exactly how, but if you look like, for example, couch surfing and Airbnb, you have one that has the incentive, you will get to know new people, blah, 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 and one puts the money inside. So,
agreed. And in general, like the blockchain space right now basically has nothing to say about intrinsic incentives. Yet it should be like the other half, right? Imagine, we have 1,000 blockchains of extrinsic incentives and another 1,000 around intrinsic. That would be amazing, right? So, and right now we're at 1,000 and 0, right? So, yeah.
You mentioned several times the automotive industry is driving AI.
Yeah.
Can you tell us a little more about great examples in this field? What are you doing with big auto OEMs or tier 1 suppliers?
Yeah.
Give an example, a real case scenario. What you just said.
Yeah, for sure. So about January of 2017, so a year and almost half ago, Toyota Research rang us up and said, hey, we see that you guys are doing AI and blockchain and have talked about data pooling and stuff. We'd love to build a decentralized data marketplace with you. And we're like, perfect, because we want to build that too, right? And like auto industry is a great example. So we actually built a prototype with them. We actually forked BigChainDB, which is the project before Ocean. It's still shipping, of course. We forked it, and in May of last year, so just over a year ago, we presented that at Consensus, and it's a prototype. The code's out there on GitHub, et cetera, of a decentralized data exchange. And it was very basic. It didn't have incentives. It was just showing how A could connect to B to C. The person who drove that initiative within Toyota, Chris Ballinger, he said, this is great. He saw lots of industry interest from friends and colleagues in other companies. So he left Toyota and went and formed a new initiative called MOBI, M-O-B-I. It was just announced about a month ago. And that has... Oh, perfect. Great. Yeah. So basically, this has like automakers that make like 80% of the cars, and more of them are coming in, and also insurance companies and other guys are coming in too. And collectively, they're going for a few things. One of them is the initiative around self-driving cars. Self-driving cars, like pooling data for self-driving cars. And there's some other initiatives too that they have. Kind of like, I think there's one related to actually mobility-ish, like Uber-ish, all that, I'm not sure. I know there was a few things that they announced at Consensus last year. One was mobility, one was the data exchange, and there was maybe one more. So they have other initiatives too, and so that's one, probably the most prominent example of sort of big players in the industry. And several of the startups are working with them in various ways, right? Another one that I'm excited about in general, I don't know if anyone's really doing this yet, but I know you're well placed for it, and that is, you can talk about tokenizing Uber, for example, right? And that's kind of interesting, but of course it would have to, like a network that's just like Uber, and there's some examples out there. But should it be just cars, right? Why shouldn't I set it up where it's, mobility as a service more broadly, so it doesn't matter whether it's cars or subways or whatever. And then in the end, what is the sort of work that's done? It's proof of moving human from A to B, right? So instead of serving up data or solving a computational puzzle, it's like I've moved a person from A to B, and maybe with trade-offs of safety and speed, right, for example, and maybe other constraints. But with that then, and you can actually track this proof of move because we have emerging protocols like Foam, which is proof of location. So every 10 seconds you get a proof of location in a secure way with Foam. And in the end, if I move you from here to 10 blocks that way on a bicycle, it's environmentally good, it's medium fast, it's medium safe, and I've earned some tokens, right? And so that's, to me, like a really cool example. No one is really going for that yet, which to me is a nice opportunity. Maybe you are, or maybe you will have to decide. Yeah. So, but I see, there could be a lot more opportunities. Kind of my broader vision of all of this is that there's going to be a lot more tokenized ecosystems than people think, right? Right now, people are viewing it with cryptocurrency lens. They're like, oh, there's only going to be 5 currencies. There's only going to be Bitcoin. That's not the way to think about it, right? It's not just about currencies. And even if it's just currencies to start with, we've got 200 countries with almost 200 currencies. But with this, we're not just tokenizing sort of currency, right? We're taking the whole cloud stack, like the 50 services of AWS. Every single one of those services is getting 5 networks, right? Or will get. But then we're going higher and higher and higher to the level of software services on top, and then the world of atoms as well, like mobility as a service, et cetera, right? So all of these things will be tokenized, right? So we will have tokenized pubs where it's sort of like a co-op, except it's tokenized, right? And wouldn't that be cool? We all collectively own a piece of the local pub that we hang out at, right? And it'll be really low friction to buy into. Or if you think that the world of craft beer is going up in general, then you can invest in 10,000 craft beer pubs all throughout the world if you want, right? Or in just Madrid, and that should be really easy. Baskets of these different things, right? Real estate, this is starting to happen, right? And all the public infrastructure that governments do, roads, and all of this can all be tokenized, and I see that happening. One of my favorite initiatives is with Estonia, right? They have e-residency, which isn't tokenized, but has the same idea of sort of like, helping to dissolve borders. But the next step, the people that did e-residency are now moving towards what they call Estcoin, which is essentially tokenizing Estonia step by step by step, right? So to me, that's super exciting. And it's not just Estonia talking about this, right? There's several governments that are moving along. And just look, any government that already has ICO-friendly regulations, they're asking what next, right? And the what next is, tokenizing bit by bit. So I know that's a long answer, but it kind of shows a broader picture. So everything basically in the mobility world will be tokenized.
Yeah, but the thing is that you're talking about infrastructure,
yeah.
You're talking about cars or even underground. These are very heavy asset stuff, right? So someone has to invest heavily in this, right? So a service, and also you mentioned service provider like Uber. But to compete against Uber, it's a matter also about user acquisition. SoftBank put about 12 billion, and now you want to compete against Uber. It's not easy because they already have the users.
Yeah.
You can make a better version of Uber, but maybe you struggle to get the user base, right?
Yeah.
So it's not easy, basically, to compete against Uber, to create fleets of vehicles because of the ownership, a heavy asset thing, and so.
Well, you know, so I mean, you know, if you think about Bitcoin, and you know, if you're following Bitcoin in say 2010 or 2011, people were like, yeah, Bitcoin is going to completely upend the banking system. It's going to rewrite the rules. And now it's sort of like, to me, it's an inevitability. It's going to happen, right? And it's happening, right? And how did it happen? With simple incentive structure at the very core, right? This simple software system that's just paying people to add security to its network of storing value or currency, right? So, and that's kind of remarkable, right? And so you can think of blockchains not as startups. Think of them as basically movements, right? Where you have sort of a founding myth, a founding story around it. You have a bunch of people with shared values that really want to change the world, and now they can participate directly. You know, even if I love Uber, how can I participate directly? Well, maybe if I'm really connected, I can buy some shares on second market or something like that. But it's really hard for me to actually gain value from Uber, from its value, right? Or Lyft or any of these guys. But if you have a decentralized Uber, every single driver can own a piece of that, right? So the drivers that are right now driving for Uber that are not getting, you know, they're getting paid, but they're not getting the profits that Uber is getting. If they actually get a higher slice of the profits, that's really cool, right? So that's a core raw incentive right there. It's still going to be hard, make no mistake, but these incentives can really play out powerfully, right? And we've seen other tokenized ecosystems go from 0 to 1 billion or 10 billion very quickly, right? Like Ethereum is worth more than Uber, and it's less than 4 years old, right? So yeah, and even the founder of Uber, you know, Garrett Camp, he's actually doing his own coin right now, right, for a currency, right? So yeah, so it's not going to be easy in general. Like there's these incumbents, and they're big and they're powerful, but they actually can't compete directly, and the blockchains can take as long as they want, because the blockchains aren't going away, right? Whereas these guys, they have to just keep competing year after year after year, being profitable to their and or growing value for their shareholders. And bit by bit by bit, the blockchain could eat them, right? So Bitcoin took its time at first. Well, you know, all good exponentials, they start slowly, they move slowly, they move slowly, they move slowly, until they move quickly, right? So, but yeah, it could be a while. It's maybe not 1 year, or maybe it's 10 years, who knows?
Yeah, because also, the thing is that with Ethereum or Bitcoin, you don't involve heavy assets and stuff, right?
Yeah.
Yeah. With Uber, you have to, because you need cars.
Yeah.
They need a real object to operate the service.
Yeah.
Yeah. And so it's not easy to make the same thing.
Yeah. Well, I mean, the thing is, the drivers themselves own that, though, right?
Yeah. Also, AI is trying to kill the driver.
Yeah. Well, on that though, actually, so I guess we are running out of time. But the quick answer to that is, the cars can be self-owning.
Yeah.
And I've written about this, and that's a whole fun other talk. If you want, I can give one more. No, I won't. One more. But no, really, and that's really the future. Like every single car is its own corporation and its own blockchain, and basically it accumulates wealth for itself, and then of course gives all its access to UBI. So I'll stop there. So. Thank you, everyone.